Good morning, everyone. It's my pleasure to introduce today BEG Seminar Series guest, Jun-Whan Lee, who is assistant professor in the Department of Civil Architecture and Environmental Engineering at UT Austin here, specializing in coastal engineering. He conducted research utilizing machine learning, numerical modeling, and remote sensing to study extreme hazard in coastal and ocean environment. His research interests include coastal hazard, storm surge, tsunamis, and compound flooding, climate and coastal resilience, nature-based solution in coastal and ocean environment, coastal vulnerability and risk assessment, and coastal processes. He obtained his PhD in civil and environmental engineering from Virginia Tech in 2021. He completed his BS and master degree in civil and environmental engineering at Hanyang University in South Korea. From 2014 to 2017, he worked as coastal hazard researcher at the National Institute of Meteorological Science in South Korea. After obtaining his PhD, he served as postdoctoral associate at the Center for Coastal Studies at Virginia Tech before joining the UT Austin in 2023. So please welcome Jun-Whan Lee. Whenever you're ready, you can start.
All right, so hello everyone, and thank you very much for the great introduction. First of all, thank you for inviting me to this BEG seminar series. And as Wanya mentioned, I'm an assistant professor here at UT Austin Civil Engineering Department, and today I prepared some presentation to show what I have been working on and what our group is working at the Coastal Hazard Lab. And before starting about the research presentation, I prepared short slides to introduce myself, but as already Wanya mentioned, I'm working on building sustainable and resilient coastal and ocean environments by better understanding coastal hazards using 3 different approaches such as numerical modeling and machine learning and remote sensing. And this talk will be focused on the machine learning part. So how can we use the machine learning to predict the coastal hazards such as storm surges and tsunamis rapidly, but also accurately and reliably. Okay, so now let's dive into the main part of this presentation. The coastal hazards such as tsunamis and storm surges, as you know, are destructive and coastal natural hazards for coastal communities around the world. The 2004 Indian Ocean tsunami and the 2011 Tohoku tsunami are prime examples of how tsunamis can cause extensive damage to coastal communities. And Hurricane Katrina in 2005, which generated a storm surge exceeding 7.5 meters above sea level, is recorded as the coastalest natural hazard in US history. And one of the key challenges in coastal environment, I believe, is an increased uncertainty and risk from coastal hazards because of the growing coastal population. So as you can see in this figure, the coastal populations have expanded at a tremendous rate over the world. Almost 2/3 of the world population already live near the coast, and approximately 75% of the world population is expected to live along the coast in the next 3 decades, which means that the coastal hazards will have more significant impact to coastal communities. Moreover, rising sea levels due to climate change are also great concerns to coastal communities, which can not only exacerbate tsunami damage, but also trigger increases in flood frequency by storm surge. This is a big problem because most of the coastal infrastructures were not developed with today's knowledge of climate change stress in mind. And Texas is also facing increased uncertainty and risk from coastal hazards because of not only the growing coastal population, but also due to the global climate change. 20, according to the survey, 24.5% of the Texas population already live near the coastal zone. And historical records show that the sea level rise at Galveston, Texas is increasing at a much faster rate than the global average. And this is a big challenge because the increased coastal risk creates a complex problem surrounding the nexus of cities, water, and energy. As shown in this figure, the increased coastal risk can affect the built environment, tourism and recreation, Gulf seafood and fisheries, ports, critical waterways, and the energy sectors such as oil, gas, and wind turbines. And these coastal challenges are not just limited to coastal counties in Texas. This figure shows the change in population distribution as sea level rises. And the blue color is the area where more people are expected to migrate. So if you look at the right figure, rising sea levels could drive more than 800,000 climate migrants to Austin by year 2100, which could be a problem if Austin doesn't prepare how to accommodate those waves of coastal migrants. And someone might wonder why we need to study tsunamis in Texas. So yes, Texas has very low chance of tsunami damage because it is quite far from the global subduction zones where large earthquakes usually occur. However, tsunamis can indirectly affect Texas by interrupting global supply chain system. For example, when the 2011 Tohoku tsunami occurred, the tsunami damage in Japan created a domino-like cascade impact on the car manufacturing industry of the United States. Then what is needed to better understand and respond to this increased uncertainty and risk from coastal hazards? Several studies have emphasized the need for a rapid and accurate prediction model that can support not only the coastal hazard forecasting system, but also a robust hazard assessment where a large number of simulations are required to account for the uncertainty in hazard characterization. For this reason, over the last several decades, a lot of research efforts have been geared toward developing high-fidelity physics-based numerical models, such as the model that can predict tsunamis from the earthquake information, or a model that can predict storm surges from hurricane information. However, there is one big challenge. The high-fidelity physics-based numerical models are computationally intensive, even though several computational techniques are employed to improve the efficiency, such as parallelization and adaptive mesh refinement. So we tackle this long-standing limitation of physics-based modeling by applying machine learning. Recently, machine learning is getting more and more attention because it is known as an effective way to complement the physics-based models to reduce the computational time. Once the machine learning finds the relationship between input and outputs, which is training based on the physics-based numerical simulations, the output can be rapidly estimated across the continuum of input spaces. However, the machine learning model has not been widely developed to predict tsunamis and storm surges. There could be several reasons, but I believe one of the main reasons is the high dimensional input and output in the tsunami modeling that requires a large number of simulations to try to apply the machine learning approach. So in tsunami modeling, the input is usually represented by 9 earthquake fault parameters, such as the fault length, width, or the 3 angles, strike dip, break angles, and so on. And if we consider 3 values for each parameter, that means about 20,000 physics-based numerical simulations are required to try to train the machine learning model, which is computationally expensive. And this is just assuming the uniform slope distribution. If we consider the non-uniform slope distribution, we might need more than 1 million simulations to try to train the machine models. And in terms of storm surge modeling, it has a similar dimensionality issue. So the input of the storm surge modeling is usually represented by the 6 tropical cyclone parameters, such as the location, direction, pressure, radius of the maximum wind speed, and so on. And the problem is that those kind of values change over time. Moreover, the storm surge responses is very different depending on the geospatial locations, and that makes much challenging to train the machine model with high accuracy. And due to this limitation, none of the existing machine learning studies has incorporated the variation of tropical cyclone conditions over time in the machine learning modeling framework. Instead, the existing storm surge machine learning models rely on a tropical cyclone condition at one moment, usually at or near landfall. And this is a problem because the existing storm surge machine learning models cannot distinguish between 2 tropical cyclones, which is represented in these slides, which have the same condition at the landfall location, but different condition before and after the landfall. And this is a big problem because historical records show that the peak storm surge is not always most correlated with the tropical cyclone parameters at landfall. So with this background, we develop a new machine learning models that overcome those kind of dimensionality issue in machine learning modeling and finally can predict the coastal hazards, tsunamis, and storm surges rapidly, accurately, and reliably. So I'd like to first introduce and talk about the tsunami machine learning models. So as I mentioned earlier, due to the large data dimensionality in tsunami modeling, we need at least 20,000 numerical simulation data to try to train the machine learning model with some traditional machine learning approaches like neural networks. And even though we get 20,000 numerical simulation data, it is not guaranteed to achieve a high accuracy. So we developed a new methodology that can reduce the data dimensionality in tsunami machine learning model framework, and thus these new machine learning models only require about 1,000 numerical simulation data to achieve a high accuracy and efficiency. So before we talk about how we reduce the data dimensionality, I want to introduce the definition of one of the key tsunami properties, a run-up. Run-up is the maximum vertical tsunami height onshore above mean sea level. And predicting this tsunami run-up accurately is very important because it is not only related to the tsunami forecasting, but also the hazard assessment. And this run-up is directly related to the level of tsunami damage. And related to the tsunami run-up, Okao and Tsunolakis did very interesting research in 2004. So they found that the along-shore tsunami run-up distribution, the black line in the right figure, perfectly fit to the empirical OS formula, the red dashed line in the right figure, in an ideal barometric condition where the water depth is uniform and the slope at the beach is uniform. However, in real barometric conditions, of course, the along-shore tsunami run-up distribution does not perfectly fit this empirical formula due to the interaction between the tsunami and the local topographic characteristics, like this figure. So after reading this paper, we came up with an idea to decompose the tsunami run-up distribution in real barometry, the black line in the left figure, into the source run-up, the red line in the right figure, which is the leading order contribution that can be represented by the empirical formula that was proposed by the Oka and Tsunolakis. And the other part, a normalized topography run-up, the blue line in the right figure, which is the residual part that is independent of the tsunami source and only associated with the local topographic characteristics. So I will skip all the details, but with this new idea, we were able to develop a new tsunami machine learning model that can predict the tsunami runoff distribution from the earthquake fault parameters like this diagram. So first, we trained the machine learning model between the empirical formula coefficient ABC and the earthquake fault parameters based on the systemically designed 1000 physics-based numerical simulation data, and extract the normalized topography runoff, the blue box, which is only representing the local topographic characteristics of the tsunami response. And once the machine learning model is trained, the OS formula coefficients ABC can be predicted from any combination of earthquake fault parameters, but within the range used in training. And then by inputting those predicted coefficients into the empirical formula, we can predict the source runoff, the red box, which is the leading order contribution. And finally, the tsunami runoff distribution, the black box, can be estimated by combining the source runoff, the red box, and the normalized topography runoff, the blue box. So with this new approach that models the leading order contribution and the residual part of the tsunami runoff distribution separately, this new machine learning modeling approach only requires about 1,000 training data to achieve on high accuracy. So to validate this new machine learning approach, we trained this new machine learning model for the northern Puerto Rico area where large tsunami can arrive within an hour if the large earthquake occurs near the Puerto Rico Trench. And we test this new machine learning model based on the 100 random tsunami scenarios that had never been used for training. And the right figure shows one example results where the black line represents the physics-based numerical simulation model results, and which solves the Bush-Nash equations. And the red line is the tsunami machine learning model prediction. And we conclude that this is quite an accurate result considering the computational time. So the computational time shows that in order to simulate one scenario based on physics-based numerical model, it took about an hour when we use 24 CPU cores clusters. On the other hand, once the tsunami machine learning model was trained, the computational time was less than a second with a single core of my laptop computer. And the difference in computational time between the machine learning model and the physics-based numerical models would be even greater if we use higher resolution grids and larger study areas than those used in this study. In addition, we believe the tsunami machine learning model has an advantage in terms of stability. Physics-based numerical models may have stability issue depending on the numerical scheme, grids, the time steps, and depending on the initial conditions, which is especially critical for real-time forecasting where lives and property are at stake. On the other hand, the tsunami machine learning model is already stable since it's just solving a simple algebraic equation. And from now on, I would like to show two example studies where this new tsunami machine learning modeling approach has been applied to improve the capacity of tsunami forecasting and also the hazard assessment. So first, in terms of hazard assessment, the tsunami machine learning model has been applied to solve one of the limitations in tsunami inversion modeling. So as opposed to the tsunami form modeling that predicts tsunamis from the earthquake information, the tsunami inversion modeling is the process to predict the earthquake information from the tsunami observation. And tsunami inversion modeling is very important to better understand the historical tsunami source and their impacts, which will benefit preparing for the future tsunami events. The basic concept of tsunami inversion modeling is to run the tsunami model several times and find the best match earthquake scenarios by comparing the tsunami model prediction and the tsunami observations. One of the limitations in tsunami inversion modeling is that although there are several high-quality tsunami run-up observation data, thanks to the tsunami survey teams, those kind of tsunami run-up observation data were not widely used because of the computational burden of high-fidelity physics-based model to simulate the tsunami inundation process. So to overcome this limitation, we applied the tsunami machine model in tsunami inversion modeling framework and called this model a TRF-IMV model, the tsunami response function inversion model. So this figure shows the case study of the 2014 Chile tsunami event. If we input the tsunami observations, if you look at the black dots in the middle points, those are the real tsunami radar observations. And if you use these data as an input, this new tsunami inversion model will find the scenarios that shows the small run-up errors between our new tsunami machine model predictions and these observations. And based on the selected scenarios that shows a small errors, these new inversion models provide two outputs. So one is probabilistic tsunami source, and the other is probabilistic reconstructed tsunami run-up distribution. In this figure, the red parts which is represented in square or the bar graph, that is representing the machine learning model prediction. And there's a black or blue parts with blue stars or the black stars and the straight line in the figure that is representing the USGS or the GCMT solution, which were estimated based on the seismic data. And we considered those values as a true value. And there's a green stars and the green line or the green dash line, which is the other study results, which were estimated based on the offshore buoy data. And the results showed that our new inversion model prediction agree well with the true value and shows even better performance in reconstructing the tsunami run-up distribution than the existing study. And now let's move on to the tsunami forecasting. So one of the key challenges or the limitations of our new tsunami machine learning model was that it was only applicable to the earthquake assuming uniform slope distribution. And this uniform slope distribution assumption is quite acceptable for a moderate earthquake like moment magnitude 8 or less. But this assumption may cause a large error for the great earthquakes where moment magnitude is larger than 8, which can affect the tsunami forecasting accuracy. So we recently improved the tsunami machine modeling framework to consider the earthquake with non-uniform slope distribution. And I didn't prepare the details how it works, but the right figure shows one example studies for the 2011 Tohoku tsunami case, where the red represents, in the right figure, the red represents the machine model prediction and the black represents the physics-based model prediction. All right, so now let's move on to the second part of this presentation, storm surge machine learning model. As I mentioned in the beginning, one of the key limitations of the existing storm surge machine learning model is that they only use the tropical cyclone condition at one moment, usually at or near landfall as the machine learning model input. And those kind of point-based input makes the machine learning model not distinguish between the two tropical cyclones which have the same condition at the landfall, but different condition before and after the landfall. So the main contribution of our work is that we develop a new storm surge machine learning model that incorporates the variation of tropical cyclone conditions over time, which allows for predicting more realistic tropical cyclone scenarios than the existing machine learning models. So, and this was possible by applying a convolutional neural network, which is one of the famous machine learning model architectures widely used in computer vision projects. The convolutional neural network allows the computer to capture the variation of tropical cyclone series like a picture. However, because the storm surge response tends to be very different depending on the areas, and the storm surge data size is very, very large. If we consider large regions, the convolutional neural network alone cannot achieve a high accuracy, and it also takes a lot of time to train the machine learning model. So to overcome those kind of limitation, we developed a new machine learning model that combines the convolutional neural network with principal component analysis and k-means clustering as shown in this diagram, and we name it as a C1P-Cannon model. So this model can be trained by following the direction of the white arrows. We first designed these machine learning models to clusters the locations which have the similar peak storm surge responses. And for each clusters, we use data dimensional techniques to reduce or extract the main components of the storm surge responses, and then train the convolutional neural network between the time series of tropical cyclones and with the principal components of the peak storm surges. And once the model is trained, it can predict the peak storm surges for the study area just by following the direction of black arrows. And to validate this new machine learning approach, we trained the machine learning model for the Chesapeake area based on the pre-computed database called the NACCS database of the US Army Corps of Engineers. So this database includes the ASCIRC coupled with the ST-WAVE, the high-fidelity physics-based numerical model simulation results for about 1,031 synthetic tropical cyclones. And by selecting a few scenarios as a test set, we validate the machine learning model based on the synthetic tropical cyclones. This figure shows the results of one synthetic scenario, which was, of course, excluded during the training process. The left figure shows the machine learning model input, which is the tropical cyclone track time series, and the three right maps shows the machine learning model prediction, physics-based model prediction, and the peak storm surge adders between two models. And the cross-validation results showed that 99% adder was less than 0.34 meters, which is quite accurate, again, considering the computational time. Similar to tsunami modeling, the storm surge machine learning models is much faster than the physics-based numerical model. In order to simulate one tropical cyclone scenario using physics-based numerical model, it can take more than several days, even though we use a multi-core high-performance computing clusters. On the other hand, once the machine learning model was trained, the computational time was less than a second with a single core of my laptop computer. And this new machine learning model was also validated based on historical hurricanes to test the capacity of storm surge forecasting. We tested for 3 hurricanes, Hurricane Isabel, Irene, and Sandy, and this shows the Hurricane Isabel case, which caused more than $3 billion in damage. So the left figure shows the hurricane parameter time series of Isabel that was used as an input of the machine learning model, and the middle map shows the peak storm surge predicted by the machine learning models, and there's a small red circles which represents the location of NOAA tide stations where we can get the water level observations. And the right figure shows the comparison between the water level observations on the x-axis and the machine learning model prediction on y-axis, which confirm the machine learning model's high accuracy in terms of storm surge forecasting. And we also use this machine learning model considering the sea level rise factors to investigate the future storm surge risk. Because there is a lot of uncertainty, not only in the sea level rise, but also in the future tropical cyclone track. We develop a framework to run this machine learning model more than 10,000 times to generate some hazard maps like these figures. Building upon the storm surge machine learning model and hazard assessment framework, we are expanding our research into the field of risk assessment, which consider both hazards and vulnerability to enhance coastal resilience. So these projects focus on the temporal dimension of coastal flood risk assessment, examining how flood occurrence during the day and night can have distinct socioeconomic implications for coastal cities. As we know, the timing of the flood event can have significantly different impact to the city's vulnerability and resilience. During the day, the consequences may differ due to factors such as population density, infrastructure uses, and transportation networks. So we are trying to develop an AI-powered daytime, nighttime coastal flood risk assessment tool incorporating the temporal dimension in risk assessment. And this will be very important because these days, the tropical cyclones that is rapidly intensifying occurs a lot, which have a short notice of the evacuation time. And this tool comprises three main parts: hazard, vulnerability, and the risk. So in terms of risk component, we apply the same C1PKNet machine learning approach to the coastal Texas areas to predict the peak storm surge from the hurricane track time series. So the left figure shows one example of the machine learning model prediction. And if the user want to use some probabilistic approach, we can use some kind of FEMA 500 flood map if they want to incorporate those kind of probabilistic approach in the risk assessment framework. And in terms of vulnerability, traditionally, the social vulnerability index has been widely used that incorporates various social economic factors like poverty level, education, and employment status within the community to access the vulnerability. And through this project, we developed a method that can break down this social vulnerability index to daytime and nighttime components using the population distribution data so that we can see how the vulnerability can be changed during the day and night. So the final outcome of this tool is the risk map that overlays the hazard map with the vulnerability map. And so the left map shows the total coastal risk, which is the conventional approach used for the decades. And the right two new maps display the daytime and nighttime coastal flood risk, where the red indicates the high risk and yellow indicates the relatively low risk. And these maps highlight the difference in risk distribution between daytime and nighttime, a level of details not captured by the traditional total risk map. And finally, we are also applying the machine learning approach to support the post-coastal hazard building damage assessment. In order to better understand the impact of coastal hazards and prepare the future events, it is very important to access the post-disaster building damage. However, obtaining the comprehensive building damage data from street level or the aerial imagery or from public records is often challenging because of the severe damage like this photo. So when we investigate the post-hurricane reconnaissance data sets, and we found that among about 3,700 single-family house records, approximately 1,200 data sets were lacked at least one piece of building information, which hinders to get some comprehensive understanding of the building damage. So we developed a new machine learning model that is using the existing building information with the reconnaissance hazard data like wind, wave, and the building damage level with the location information to predict the missing building information. And that shows the preliminary results, which shows what kind of structure features this machine learning model can predict. And the right scatter plot shows one example of the prediction. So we intentionally hide some of the building age information and use the machine learning model to predict the building age by using the hazard information and known building information. So the x-axis is the machine learning model prediction, and the y-axis shows the observation data sets, which was hidden during the prediction process. And this figure shows the feature importance for each components to predict each of the structure features. And I want to emphasize the blue part which is representing the hazard information. So in this machine learning models, this model requires the hazard information, the storm surge and the wind, which is coupled with the building damage level, can be used to reconstruct the structure features of the damaged building, so the hazards can be used to reveal some of the missing data information. And with that, this is the end of my presentation, and thank you very much for your attention. I will be happy to answer any question.
Thank you very much for your machine learning or your research. So, any question to Dr. Lee? So I have a question for the daytime and nighttime. I mean, risk, coastal risk stuff. But so can you? So when you incorporate daytime and nighttime coastal risk, just summation both index or some different approach for total flood risk for daytime and nighttime.
That's a great question. So currently, we are just supercomposing with the hazard, with the vulnerability, but because of the interdependence between the hazard and the vulnerability vectors, there's a nonlinear factors we need to incorporate. That's one of the future direction that we want to incorporate, because if there is a hurricane event, it will be different from the normal day, the sunny day vulnerability. So we are trying to find a relationship. How can we incorporate the difference, the interdependence of the network systems and the social vulnerability systems that will be changed during the extreme event conditions?
Okay. So another question is the for your machine learning techniques, forecast how many, how many hours, how many days in the future your machine learning technique can forecast in the future? I mean, in terms of preparing the evacuation, something like that.
So for both tsunamis and storm surges, we do not have any limitations. So if there's an earthquake information, we can make a tsunami prediction right away. And also, if we have an estimation for the hurricane track, we can apply that track information to our machine learning models. So once we get those kind of input data, we can make any kind of prediction based on that input data. But of course, there will be uncertainty.
So, right. Okay, any other question?
One here, I think John Melito had a question.
Oh, yeah. Okay.
He had his hand raised.
Okay. Hey, John, please.
Hey, yeah, sorry about that. I was clapping, but I'm wondering if there's I mean, I wasn't actually asking a question. I was just clapping from the audience, but I'm wondering if you've thought about implementing other things like relative sea level rise, like we were talking about earlier, hugely impactful on the Texas coast. Has there been a thought of adding that or adding any other kind of coastal stressors or climatic stressors to these models since they perform so well?
Yes, so currently the storm surge machine learning models only incorporate the pure storm surge. So the future direction is to, of course, incorporate the sea level rise, also all the compounding effects of the coastal hazards. But one of the limitations of the machine learning approach is really requires a lot of data to achieve a high accuracy. So we are our research is not just focusing on applying the machine learning. We are trying to find a way to reduce the required number of training data sets to achieve a same accuracy that requires a large data set. So we are trying to figure out how we can do that using some, not only the machine learning approach, like a data dimensional reduction techniques, but also using some domain knowledge that we can apply to our field.
Thanks.
Thank you.
Julia?
Hello, can you hear me?
Yeah, sure.
Okay, so I actually just typed my chat question in the chat as well. So for the upcoming hurricane season in the Gulf of Mexico, are you intending to do a prediction in real time, assuming that we get a fairly decent sized hurricane? And then the follow on from that is, I'm assuming when you do that, it'll be a kind of an academic exercise so that you're improving your modeling and getting more information as to how well you did. But at what point do you think you're going to be ready to give predictions to authorities in charge of things like evacuations and response and FEMA and people like that?
That's a great question about how the real application would be looks like applying those kind of machine learning approaches. So we are trying to make a real-time forecasting systems that, of course, use for the academic purpose, but in terms of the real evacuation decision making, that requires a lot of trust issues.
Yeah.
And one of the limitations of the machine learning approach is that kind of black box. So we are trying to streamline our research scope to apply the physics-informed neural networks to make another model that can be explain what's going on inside of those rapid machine learning approach. Then maybe that could be used for the final decision-making policymakers to use that information to their policy or evacuation orders and so on. So those models are currently designed for the academic purpose, but we are moving toward that direction to be used for any kind of real applications. So
Yeah, thank you. Excellent talk, by the way. Thanks.
thank you.
So any other question? So yeah, Yongcher Choi, you have a question?
Yeah, thank you for your presentation, Mr. Dr. Lee. And I have a question about another, you can hear about other pieces, but have you ever thought about ecosystem of this after tsunami? I mean, not about the coastal hazard of humans, but, you know, about after coastal hazard, about eco tsunami or something about it.
So I didn't hear well about the system. So are you asking about?
He asked about ecosystem, right?
Oh, so how the ecosystems will be impacted by the tsunami? Yeah, that's a great question. So one of the interesting part of the coastal hazards is that it's causing a damage to human lives and buildings, building infrastructures, built environment, but it has some positive impact to the ecosystems. It is mixing the coastal waters and it's also providing or relocating the sediments. Sometimes it's causing erosion, but some parts it's causing a deposition. So we are trying to explore that kind of positive impact of the coastal hazards. What can be the part that is giving a positive impact to the ecosystems, but that's one of the future directions that I want to explore. Thank you for pointing that out.
Thank you.
This is my last question. The UT love the digital twin stuff, so I wonder, is there any extra work research regarding the digital twin or coastal digital twin in your group?
Yeah, that's a really hot topic, and we want to incorporate the real-time sensing data from the water levels or the RGB cameras that are installed in the beach that could be incorporated to our modeling to fuse the data to make an updates on our models. That's one of the directions that we want to explore. And I'm collaborating with another professor who is an expert in digital twin, who are trying to use the build environment or the energy grids or the building information to incorporate to our simulation data sets to give more information on how to make a good decision on their purpose for evacuation or to relocate people, or where we need to prepare some resource for the recovery process and so on.
Okay. No more question? Okay. Thank you very much today, Dr. Lee. See you next time.
Thank you.
Bye-bye. Bye-bye, everyone.
Thanks.